So we're going to get into the beginning of chapter 11, and I want to review just for a second what we did in chapter 10, because the very first part of chapter 11 is almost a redo of chapter 10. And so if you did well in chapter 10, you should be in great shape in the beginning part of chapter 11. If you struggled through some of chapter 10, then now's your chance to overcome. So we started out in chapter 10 and we talked about normal distributions. And I told you that if we had, say, an alpha level of 5%, then each of these regions was 2.5% based on some original mu. So what does it mean that alpha is 5%? Okay, so our type 1 error is 5%. What does it mean that I'm going to make a type 1 error? All right, so there's two parts to it. The first part is I'm rejecting this original belief. But the second part is the original belief is true. That's why it's an error. So it's not only am I rejecting out here, but I'm doing so mistakenly. So we know if I did something over and over and over again where that was actually valid, some of the times my answers would tell me to reject that even though it's true. That's what the 5% type 1 error is. It means that I'm going to tolerate screwing up as much as 5% of the time. Now, we'll take a brief aside into a short history lesson and talk about a fellow named William Gossett. And William Gossett lived in the early 1900s, and he worked at the Guinness Brewery in England, and he worked with essentially quality control. He did a lot of stuff with quality control, and Guinness prided itself on having a good product that was consistent. And so he would test the product, he'd test the barley as they made the beer, and make sure that it was up to stuff. Well, he figured out over time, and it must have taken him a long time, that using this idea wasn't working very well. He figured out that these errors were happening more often than they ought to be happening, and he couldn't figure out exactly what the deal was, and he must have spent forever on it. Can you look at the formula here and figure out what the problem is? What's the problem with this formula? Coach Wise, there's a problem. We just used it for a whole chapter. All right, so we don't know X bar, right? I mean, we can figure out an X bar, but X bar is not always the same. When you do it, when I do it, when she does it, when the other person does it, we all get different X bars. And that variability, the variability between my X bar and your X bar, is what's giving us a difference. And it's the variability there that causes us sometimes to reject HO erroneously. But we handled that back in chapter 10. So what else is going on? Standard deviation is exactly right. We don't know mu or sigma, but we set up a hypothesis test talking about, hey, what if mu is 17 or some number? The problem is at the very end, when we get a small p-value and we reject HO, it might be because this presumption was wrong, but it could also be that this sigma is not really sigma. Because where did we get sigma? Somebody had to tell us, right? And in real life, who tells us? The statistical all-knowing God? Probably not. We don't really know sigma. So not only are we assuming that we know mu and shoving it in there, we're assuming we know sigma and sticking that in the formula, but it really isn't right. So what Gossett started doing was he decided to use a formula like this: X bar minus mu over S divided by the square root of n. Because we can figure out S. We just look at our data and figure out the standard deviation of the sample. The problem is your S and my S and her S and the other person's S will all be different, just like the X bars were different. Therefore, introducing more variability into the problem. So Gossett found that we end up with a distribution that looks something like this. So the new distribution is actually more like that. Let me draw a couple of them on a new page for you. So the normal distribution looks like this, but this new distribution that Gossett came up with looks more like that. It's a little bit flatter. It's still symmetric, just like the other distribution, but it's a little bit flatter with more area out on the tails. That area out on the tails is because we've got more variability. Not only do we have variability introduced with the X bar, we have variability introduced with the S as well. Previously, Guinness had another employee publish some of their trade secrets. And so they were very concerned about this, and they passed a policy in the company that nobody could publish anything. Didn't matter what it was, you couldn't publish anything if you worked for Guinness. Well, Gossett recognized that what he was doing here was related to some important statistical stuff, and so he talked to another statistician friend of his, and they published it in his journal under the pseudonym, the very original student. So this distribution became known as the student's distribution. And in time, it became known as the student's t-distribution, or more simply, just the t-distribution. I've made copies of Gossett's t-distribution table, and I'll pass it out. It's on green paper because it's the green t-distribution. Okay, so looking at that distribution that I just passed out, basically what Gossett did is he came up with this distribution. He sent it to another fella, Fisher, who was kind of big in the creation of statistics, and he said, I'm sending you this because you're probably the only person on the planet who will ever use it. And Fisher recognized that it was actually pretty valuable stuff, and he's the one that came up with this actual t-test statistic. So Gossett came up with the table, which must have taken quite a while. Looking at the table, what are some differences you see between that and the table of your z distribution? Okay, it's got an infinity down there at the bottom. Look at the very bottom row where it says infinity. You should notice that the numbers next to the infinity row are familiar to you. 1.645, 1.960, 2.326, those are your z-stars. And the reason they are your z-stars is this. As n increases, what's going to happen to x bar? It doesn't increase or decrease necessarily. It gets closer to mu, exactly. X bar will get closer to mu. What happens to S then? It gets closer to sigma. Our estimates, our statistics, like X bar and S, get closer and closer to the real values, like mu and sigma. Now what that means is our Z table, maybe I'll do this in red, our Z table, look, X bar minus mu over sigma divided by the square root of n, and the t distribution says X bar minus mu over S divided by the square root of n. So as the sample size gets bigger and bigger, S gets closer and closer to sigma, so T gets closer and closer to Z. And so down there at the very bottom where that infinity is, that's saying I have a really big sample size. So T and Z are the same, which is why your book in the last chapter said you could be using this chart to get your Z-stars. I didn't teach it yet because I didn't want to teach this chart yet. Now from this, the next thing is you could actually have lots of t distributions. Here's another one, goes in here. You could have another one that's even flatter. The z distribution is this one down here. The sample size of this t distribution is greater than the sample size of this t distribution. And I'll show you in a second how we delineate that. So let me give you an example of a problem that we can work through and talk about how all this will relate to chapter 11, because like I said, it's very, very similar to stuff we did in chapter 10. This problem was given to you on your last test. I said, suppose that my Ford Ranger in 5 fill-ups has these miles per gallon. Type these numbers into L1 in your calculator. After you get these numbers typed in your calculator, do one bar statistics to come up with the X bar, the S, and the N. Okay, so you should get an X bar of 15, what is it, 15.874? And this is point, what's the standard deviation? And N is 5. Now, in chapter 10, the formula for a confidence interval was X bar plus or minus Z star times sigma over the square root of N. So tell me what it's going to be for chapter 11. X bar plus or minus T star times S over the square root of N. So what I want to do is I want us to come up with a 90% confidence interval for this problem. So what I want to do is look at a 90% confidence interval on this chart. And if you notice on the chart down at the bottom, you see where it says 90% confidence. This 1.645 is what I would have used with my Z distribution, but I'm not using a Z. So I've got to figure out which one of these numbers to use, and it's related to this DF business. So let's take an aside and talk about the DF business for just a second. Anybody remember what that stands for? No, apparently is the answer. It stands for degrees of freedom. So as a quick review, the degrees of freedom are the fewest number of things that you have to know before you know everything. So if I've got Alice, Bob, and Charlie, and between the three of them, they have $5. How many of those people do I have to tell you before you know how much they all have? Obviously just 2 of them. If I tell you 2, you know how much the third has because they all add up to $5. So now we've got to review this for just a second. Standard deviation is a measurement of spread. It measures spread. In particular, it measures how spread out the numbers are from the mean. It is from each other, but each other based on the mean. So it's how far each of these numbers differs, in this case, from X bar. So you might remember back in chapter 1, the way we did this the long way is we'd type all of these numbers into L1, we'd find the mean, and then in L2, we'd take all of those numbers minus the mean. Do you remember what that column summed up to? 0. It always sums up to 0, and that's why we had to square it and keep going through the rest of the deal. But if the sum is always going to be 0, then all I have to do is know all but one of those items, and I can figure out what the other one is, because it's whatever number would help it equal 0. So for the sake of what we're doing today, the degrees of freedom are n minus 1. I don't, however, want you to get the habit or get in your mind that the degrees of freedom are always n minus 1. The degrees of freedom are how many things you have to know before you can figure everything else out. If you thought about a Sudoku puzzle, and there's 81 little boxes on there, but they might only tell you 9 numbers. And from those 9 numbers, you can figure the rest of them out, right? So for that puzzle, the degrees of freedom would be 9. It's the fewest number of things you need to know before you can figure them all out. For these problems, and in particular, for this problem, the degrees of freedom are going to be 4. So I look on my green chart for 90% confidence up this row till I get to 4 degrees of freedom, and there's the number right there, 2.132. It's n minus 1, so I had 5 items, and this was 5 minus 1, which is 4. Gossett made the table. X bar is 15.874 plus or minus, what did I say, 2.132? 2.132 times 0.5706 over the square root of 5. Now, just for practice, work that out. Make sure you know how to do that. Now, sort of as a check, I'll show you this on your calculator. You can press Stat, Test, and go to the one that says T interval. Might be number 8, depending on your calculator. The data is in L1, so I can just list the data in L1. Frequency is 1. Change the confidence level to 90%. Hit calculate. Here's my interval. I'm 90% confident that the true average miles per gallon of my truck is in that interval. Now, if you're doing this on a test, you still have to be able to show me the work. Most notably, you have to show me the numbers, the formula with the numbers plugged into it, and I'm particularly going to be interested in that 2.132. You can see the other numbers from the calculator by doing the function because it calculated the 1var stats while it did it. So you would have had to type 1var stats, it just calculated it from the gig. So now let's look and see what this would be with a hypothesis test. So I'm going to set up, when I bought the truck, the guy told me the car got 17 miles per gallon. I think I might have been taken for a metaphorical ride. And the actual miles per gallon is less than 17. So I want to know, this data right here is a really small sample size, and it's certainly less than 17. But since it's such a small sample size, is there enough evidence, we'll say at the 1% level, for me to reject that? And the reason I'm going to set alpha down here kind of low is because if I think I was snookered, I might just call the guy and tell him what I think. And so I want to be pretty confident before I go out on a limb and do something like this. So I'm going to draw my graph. I'll do it with green. And what I didn't show you a second ago is to delineate or to denote that this is a t-distribution, we put a little t down there, and then we put a subscript with the degrees of freedom. So that would be degrees of freedom of 4. If I was back on this original thing over here, I might say that this was degrees of freedom of, say, 50, and this might have been degrees of freedom of 20, and this could have been degrees of freedom of 5. You can see the bigger the degrees of freedom, which means the bigger the sample size, the closer the t-distribution is to the z-distribution. So let me draw the rest of this stuff. My center here, the center here is 17. My x bar, you remember, was 15.874. The standard deviation was 0.57 over the square root of 5. And this shaded area that I made blue right here is going to be my p-value. So now instead of using my z-test statistic, I'm going to use my t-test statistic. And the t-test statistic is x bar minus mu over s divided by the square root of n. So that's 15.874 minus 17 over 0.5706 divided by the square root of 5. And we're going to type all that in the calculator to make sure we know how to do it. So I end up with a z-test statistic of negative 4.413. Now what I'm going to do is look on my chart. Remember, there's 4 degrees of freedom, so I go across until I find that 4.413. And I see that 4.413 falls in between these two values. So since it falls in between these two values, I go up and find that my p-value then is going to fall between 0.005 and 0.01. Now, many a young stat student has said, look, coach, the 0.01's first. Can I write this? Like, no, you don't understand how inequalities work. The alligator eats the bigger thing. So then they say, well, can I write this? And I say, sure. And then somebody says, yeah, but you got the big number on the left. Okay, well, then write it the way I wrote it the first time. And certainly don't write something dumb like this. Okay, so not that anybody's ever done those things before, but those 3 things on the right are not correct. I find my p-value is somewhere between 0.005 and 0.01. So when I come back here, I will write down that my p-value is between 0.005 and 0.01. So what do I do at the alpha equals 0.01 level? Good, I'm going to reject. Blah, blah, blah. Now, obviously, today I'm not going through the conditions. The conditions are the same conditions that we've done in the past. You've got to check the shape. You've got to talk about standard deviation. You've got to talk about sampling method. I'm not going through defining my terms and writing a formal conclusion. I'm just showing you how it's exactly what we did in the last chapter with a different chart. So just to show you that I did it, stat test. The second one here says t-test. I've got the data again, mu17, list is in L1. We're doing the one-sided less than test, and now calculate it. Of course, the calculator gives you the exact p-value of 0.0057878889. It gives you a few more digits on everything. I don't care which method you use. You're welcome to use the chart or the calculator, but I do expect you to at least understand how the chart works. You must understand how the chart works. Then if you want to use the calculator, go for it. Some of you use the Cdf function just like the normal CDF function, and that works like this. Cdf of a lower bound like negative infinity, comma, an upper bound, negative 4.413, and then you've got to stick degrees of freedom on there. So stick degrees of freedom on there like that, and then it works just like it worked with the normal CDF. So now I want to show you a two-sided test. Before I do that, I mentioned a second ago that the chart shows the right side shaded, unlike the pink chart, which showed the left side shaded. That's why there's no negative numbers on your chart. You just have to be clever. Just turn it over, and they'll be negative, right? We don't really turn it over, but it's symmetric. So all those numbers can be negative. It gives me the same deal. All right, so let's look at one brief two-sided example. And in this example from my book here, researchers investigating fetal growth measured the length of the femur in developing male and female babies at 24 weeks gestation. Now let's just suppose that we know that the true femur length at 24 weeks for a female is 44 millimeters. And we want to do a test to see, is it 44 or is it, sorry, not equals to 44 for this particular population. So they went to the population and they got a sample of measurements. They sampled 270 random female babies and came up with a mean femur length of 43.42, and the standard deviation for these babies is 2.64, and this is all in millimeters. So my graph, which is green, has a it's the t distribution with how many degrees of freedom? 269. The center of this distribution is 44. It's a two-sided test. On the left, I write 43.42. On the right, it's 44.58. Where'd the 58 come from, Coach? It's the distance that I have between 43.42 and 44. So it's the same distance over there. And this shaded area here is called the p-value. Good. This is 2.64 over the square root of 270. Now, I always think it's a good idea to try to put the brain to work and surmise what sort of answer you might get. So how weird is it if the truth is 44 that I would get an answer way over here at 43.42? That's about a half a millimeter different, which isn't very much, but they're babies, so I don't expect the numbers to be very big because they're all pretty small at 24 weeks. So you're kind of thinking through this process. So let's continue with the work. The formula says it's t equals x bar minus mu over s divided by the square root of n, which is 43.42 minus 44 over 2.64 divided by the square root of 270. And then you're going to continue and figure this out on your calculator. Here I get a z of negative 3.61. sorry, a t of negative 3.61, thank you. And I'm going to look over here at my chart, and I'm going to find 270 degrees of freedom, sorry, 269 degrees of freedom. Unfortunately, that number is not on my chart. So the question is, what do I use? Well, if you look at a particular column, just pick a column and look at it, you notice the numbers get bigger as you move up the column. If you're dealing with a problem like this, what is the default that you want to go to? So using the next smallest degree of freedom of 100, I'll slide across that row looking for 3.61. And you see that it's past the end of the chart, which means my p-value is smaller than 0.005. So I'm going to write that the probability that I get a t-statistic less than negative 3.61 is less than 0.0005. However, this is a two-sided test, so I need to double that to find out that my p-value is actually less than 0.0010. So at most significance levels, like an alpha at 0.01, or most typical alpha levels, I'll end up rejecting HO since my p-value is less than alpha. If you're doing this on the calculator would be able to do 269 degrees of freedom. So when I type all this stuff in using stats this time, the calculator will automatically choose the correct degrees of freedom, and it'll also automatically double if I double that area to find the p-value if I select not equal to. So this is giving me the more accurate degrees of freedom, 0.000365, which is certainly less than 0.0010. That's the introduction to section 1 of chapter 11 and how the t-table or the t-distribution works with a confidence interval, with a one-sided hypothesis test, and with a two-sided hypothesis test.